Okay, in section 4.1, we are talking about exponential functions. So an exponential function is defined by this equation right here, where you have f of x equals b to the x. Okay, so an exponential function is basically any function that has a variable in the exponent. Okay, so a variable in the exponent. So just a quick example problem here. The exponential function f of x equals 42.2 times 1.56 to the x models the average amount of time spent, f of x in dollars, at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours at a shopping mall? Okay, so we have our equation here. Okay, where x is going to represent hours. Okay, it says f of x is the amount spent, and then x is going to be your hours. So we are told we have 3 hours here, so we're just going to change this x to a 3. Let me get the eraser there so you can actually read that a little bit better. And then we're going to go through and do this. So one of the main things that I do see mistakes with when we are looking at exponential functions is just not following order of operations. So I just want you guys to remember that exponents are going to come before any multiplication. Okay, so remember in order of operations, grouping, exponents, multiplication, division, subtraction, addition, exponent comes before multiplication. So I would want to do 1.56 to the third power first. So let me bring over the calculator here. So 1.56 to the third. That would give us 3.796, and then multiply that, so just hit times 42.2. And that's going to give you 160 and then 21 cents. So the average amount spent is $160.21 after 3 hours. All right, so let's talk about the graphs of an exponential function real quick. So you have the domain for an exponential function is going to be all real numbers. The range is going to be positive real numbers. Get a graph here. All exponential graphs are going to pass through the point 0, 1. You're going to have a horizontal asymptote of y equals 0, and then let's just take a look at these graphs. So if I want to graph 3 to the x power, go to y equals, clear if there's anything in there, and then it would be 3, then your exponent button, your chevron here, to the x. Okay, and then I'm also going to scroll down, and I'm going to do -3, and then to the x. And I'm going to hit graph. Okay, and then this is what my exponential functions look like. So that's your positive 3 to the x power. This is your negative 3 to the x power. So notice here that we have an asymptote of y equals 0, so we're going along this line here for both of these. Your domain is all real numbers, so it looks like this cuts off a little bit, but that just might be the calculator. If we look at this on graphing technology like Desmos, you might be able to see that just a little bit better. So let's take a look. You've got 3 to the x. Okay, yeah, if we look at that, you're going close to 0, and if you click on it too, you'll start getting those points. Okay, so you've got this horizontal asymptote of 0, and then you're going to go up here through the point 0, 1, and then you're going to keep growing exponentially there. So the domain is all real numbers, okay, left to right. The range would be 0 to infinity, because I'm not going in the negative aspect. Now, if I take this and I make this graph negative, it flips. Okay, so see how it flips? Well, now your range is going to be from 0 to negative infinity, or negative infinity to 0. Okay, and then instead of passing through the point 0, 1, we're going to pass through the point 0, -1. And let's take a look at some other graphs here. So if I have the graph 4 to the x plus 4 plus 1, we want to graph that. Now, typically we would want to put this in a graphing calculator, but you can graph these by hand. All you have to do to graph these by hand is create a table of values. So I do want to go over that real quickly because I know there are a few of you who do not have a graphing calculator. So if I want to create a table of values, I'm probably going to want about 2 or 3 values here. So let's try -1, 0, 1 and see what we get here. So -1 would give us, let's see, a 4, put it over here, to the -1 plus 4, and then plus 1. So -1 plus 4 is 3. So this is going to be 4 cubed plus 1. So 4 cubed is 64, plus 1 would give us a 65. So it's going to be a really high point there. Let's see what we got here. For 0, you've got 4 to the 0 plus 4 plus 1. So 4 to the 4th plus 1. Let's see what that's going to be. 4 to the 4th power is 256. Plus 1 is going to give us 257. And then for 1, you've got 4 to the 5th. Well, 1 plus 4 before the 5th. Sorry, I skipped a little step there. So 1 plus 4 plus 1. So 4 to the 5th plus 1. So 1025. All right, that's going to be hard to put on this graph if we do this by hand. -165 is still up here, and it is rising as we go up. So let's try and get closer. Let's go a little bit further back. So I'm going to do -5 and -4 as well, so I can get some points. All right, so let's see. Let me just erase this here. All right, so if I plug a -5 in, I'm going to get 4 to the -5 plus 4 plus 1. So -5 plus 4 is -1. So 4 to the -1 plus 1. 4 to the -1 is 1/4. Okay, if I put that in my calculator, okay, because it makes it fall into the denominator, and then plus 1, I'm going to get a 1.25. Okay, I can graph that on here. And then here I've got 4 to the -4 plus 1 plus 1. That's going to give me 4 to the, sorry, this is 4. There we go. 4 to the 0 plus 1. 4 to the 0 is 1 plus 1, 2. Now I'm getting numbers I can graph. So -5, 1.25, maybe about right here. -4, 2, maybe about here. Okay, I know -1 goes up to -65. That's way up here. So maybe let's see what -3 is. Just real quick here. 4 to the -3 plus 4 plus 1. So 4 to the -3 plus 4 would be 4 to the 1st, which would be 4 plus 1. That would give us a 5. All right, so the graph's going to look like that. It's going to start curving here. So we're thinking we're going to go up. We're going to go like this. And oh gosh, this thing is hard to draw the graph on. I'm sorry. That's just so bad. I can't draw a straight line with this thing. Maybe with my mouse it'll be easier. Hold on. Let's try it. There we go. Okay, so we're going to keep going up like that. And this I actually want to fix because it's not going to go past 1. All right, and I know that because of looking at this. Okay, it's going to have shifted up 1. So this line right here is going to be my horizontal asymptote. Now let's check this in our graph, and I like using Desmos when we're looking at these. So 4 to the x plus 4 in there, and then there we go. I want in the exponent. Hold on. All right, 4 to the x plus 4. Parentheses. There we go. Maybe that will help. Plus. Yeah. Hold on a sec. There we go. Okay, and then plus 1. All right, so if I take a look at that graph, similar to what we looked at. So here is your asymptote at y equals 1. Okay, and then we're going to have our points here, -5, 1.25. There it is, right there. Then -4, 2, -3, 5, and then we keep going up. All right, so then here we would want to name the domain, the range, and any asymptotes. So our domain here is going to be -infinity to infinity. Okay, that's not going to change for any of these exponential functions. The range, okay, our lowest value here was 1, so it's going to be a range of 1. And did we actually have the point 1? Let's take a look here. Maybe we can look at our table. And let's see, -10. So we're not getting down to 1. Oh, we do. Okay, so as we get further to the left, we are going to the point 1. All right, so we're going to have a bracket at 1, and then we're going to go to positive infinity. And then we have that horizontal asymptote right here at y equals 1. Okay, so carrying on a little bit of the things that we did in chapter 3 with some of the polynomial functions. All right, another exponential function is natural base e. So natural base e is defined as this equation here. So 1 plus 1 over n to the n. Okay, e is going to be the number that this approaches as it gets larger and larger. So e is similar to pi in that it actually stands for a number. Okay, so as the number here we plug in gets larger and larger, this is what e is going to approach. So this is what e is approximated to, 2.71828, 1828, 1828, etc. There is a button for e in your calculator. Okay, if you look at it, go to the left of 4, you're going to see the ln, and then in yellow, e to the x. Okay, so if you turn your calculator on and you go second ln, you'll get the e coming up there. Notice it automatically prompts you to put an exponent in. So e is an exponential function. And if I put e to the first, I'm going to get this number here, 2.71828, 1828, and then that will keep repeating. This is called the natural base. And then any function with an e in it is called a natural exponential function. Okay, so let's look at some examples here. So the first one, we have our exponential function f of x equals 1066 e to the 0.04, models the gray wolf population of the Western Great Lakes, x years after 1978. Project the population in 2012. Okay, so we have the function. There should be an x here. For some reason, that did not print out. So 0.04x. Okay, so here's our function, and let's see what this means. So f of x is the population. Okay, so the function models the gray wolf population. X is going to be years after 1978. Okay, it's telling us that right here. So we want to do the population in 2012. So 2012 is how many years after 1978? So we'll do 2012 minus 1978, and that is going to give us 34 years. Okay, so we're going to plug a 34 in for this x. Is it 0.042x? Let me pull up my original Word document. Okay, yes, you are correct. Okay, so 0.042x. Thank you. So let's see here. So 0.042. Okay, and then we'll plug the 34 in right here. All right, so with the e function, the good thing about the calculator here is you can put this in the calculator just as is. So this would be put in like this, 1066, second e, and then in parentheses, 0.042 times 34, close the parentheses. So there you get 4,445.6. So cannot have 0.6 of a person. So actually here I'm going to, well, it's just a projection, we'll round up. Okay, so 4,446. It's not a person, a wolf, but still the same rule applies. You're not going to have a decimal of an actual animal. All right, and then you do need the help of your calculator for example 2. You can make a table of values. This one we're going to go ahead and put in our calculator. So I want you to go to y equals clear, scroll down and clear. So you're going to put e in, so second ln, and then your e in parentheses, you're going to have x minus 5, close parentheses, and then plus 4. Okay, then you're going to hit graph. And then that is what our graph is going to look like. Okay, and if you want to do a couple of values here to graph it on your table of values, second table, let's see what we've got here. So it looks like we are going along that 0.4 here for our y's. And then let's see, we have the 0.55, 6, 6.7, 7, 11 point something. So let's see here. So 5, 5, 6, 6 point something, 7, it goes up to 11 point something. So roughly like this. So let's see if I can attempt to draw this here. All right, so we're going to go along the 4 on this side, and then we're going to go up through here. That looks much better with my mouse. Okay, and then we would want to do the domain, the range, and any asymptotes. So the domain here is negative infinity to infinity. Our range, okay, we're going to straddle that 4 on the y-axis, so 4 to positive infinity. And then we do have an asymptote right here, along this line here, of y equals 4. Okay, and we're going to get that from right here. That's just a shift vertically. All right, so let's take a look at how you can actually use this stuff in real life. So, compound interest. So, compound interest is a monthly, typically, interest rate. It can also be yearly, weekly, daily, things like that. So, this is your formula for compound interest. So, you have A equals P times 1 plus R over N to the NT. So after T years, so T is going to stand for time in years. A is the balance in the account. Principal P, that's what you start with. Interest rate R, that's in a decimal form. And then N is compounding periods. So if you have yearly compounding, that N would be 12. If you have weekly, that would be 52. Monthly would be 12. And there's a couple others as well. You also have continuous compounding interest, which is slightly different than periodic, this is periodic interest here. These are set periods that interest is going to be compounded. Continuous compounding is compounding at any given time. And what compound interest is it is interest that is calculated on the amount of money in an account, okay, plus any other deposits, okay, whereas simple interest is only on the original amount in the account. Compound interest is the amount of money in the account at the time that it compounds. Okay, so that is our compound interest formula. Let's go ahead and use it. So Jeff has decided to invest $2,345 into a compound interest account. He's been offered a rate of 1.65%, but is unsure of what compounding period to select, monthly or continuous. Help him figure out what will yield him the most money after 6 years. Okay, so let's get the information out of here, what we need. So we are investing $2,345. So that is our P, our principal amount, what we're starting with. Okay, his rate, R, is 1.65%. So as a decimal, that's going to be a 0.0165. Compounding periods, he is going to possibly select either monthly, so that would be 12 times a year, or continuous, which will be a different formula. So we're going to actually do two different formulas here. And in time, in years, we have 6 years. So our T is going to be 6. So let's first start with the monthly compounding. We plug these numbers into our formula. We'll have 2,345 times 1 plus our rate, 0.0165, over 12 for our N, to the 12 times 6. So order of operations is really important here. You want to make sure you do inside the parentheses first. So 0.0165 divided by 12. Okay, then add that to 1. So it's going to give you 1.001375. Okay, then you want to make sure you do your exponent before multiplication. So 12 times 6 is 72. So we're going to take this and we're going to raise it to the 72nd power. And then we're going to multiply that by 2,345. Okay, so we're going to get $2,588.86. So we did this first. Then we multiplied. So the amount after 6 years in this account, 2,588.86. All right, then we want to look at the continuous account. Joel, you have a question, you can type it into the chat box. All right, so the continuous account, we have a P of 2345. Then we're going to use the E, and then our rate, 0.0165, and then our time is 6. And we can go ahead and put that in our calculator just like that. So 2345, second E, and then 0.0165 times 6. And that's going to be 2589.04. Okay. So which one will help him which one will he choose? So this is only a difference of not even a whole dollar, it's 18 cents. Okay, but after 6 years, he's going to have more money in the continuous interest. So if he is planning on keeping the money there for a lot longer, then he would want to keep it there. After 6 years, probably not going to make much of a difference, but possibly 10 years, 20 years down the road, then it will be a little bit more. Okay, so let's work with this again with some periodic interest in example 2. So we have find the accumulated value of an investment of $13,200 for 5 years at an interest rate of 4%, and then we have 4 different compounding periods. So our P is going to be this 13,200, 5, that's our time. Interest rate 4%, that's going to give us an R of 0.04. Okay, so if I do each of these, semi-annual, that's 2 times a year. Quarterly, 4 times a year. Monthly, 12 times a year. Daily, we go with 365. All right, so semi-annual, you're going to go P, so 13,200 times 1 plus our rate, 0.04, over n of 2 to the 2 times 5. So inside the parentheses, we would work first. 0.04 divided by 2. Add that to 1. You get 1.02. And then you're going to raise that to the 10. So then you're going to do 1.02 to the 10th, and then multiply it by 13,200. So 1.02 to the 10th times 13,200. That's going to be $16,090.73. All right, we're going to do the same thing, but now with quarterly. So instead of having the 2 there, we're going to use a 4. So our A, 13,200, 1 plus 0.04 over 4 to the 4 times 5. So then inside the parentheses, I do 0.04 divided by 4. That's 0.01. Add a 1. So 1.01. So now I have 13,200 times 1.01, 4 times 5, 20. So 1.01 to the 20th. Then take that, multiply it by 13,200. So that's going to give you $16,106.51. All right, now monthly, we will now have an N of 12. So 13,200, 1 plus 0.04 over 12 to the 12 times 5. All right, so order of operations, we're going to do 0.04 divided by 12. Then we're going to add that to 1. Okay, so that's 1.003 repeating. 12 times 5 is going to give us 60. Thank you, Edwin, for answering that question in the chat. Okay, now here, when you do have a repeating decimal, it's important to try not to round until the very end. So here, I'm just going to make sure that I keep that in there and I do raise it to the 60th. And then I multiply by 13,200. So there I get $16,117.16. All right, and then the last one we have daily, so that is going to be 365. So 13,200, 1 plus 0.04 over 365 to the 365 times 5. So before I do the parentheses, I'm going to do 365 times 5 so I know what that is. So it's 1825. All right, so now I'm going to do 0.04 divided by 365. Then just go plus 1. Okay, you have your decimal there. Leave it in there. Okay, so now that is 1.0, and I just write ... because I'm going to leave whatever's in the calculator, and that's your 1875. Sorry, 25. Okay, then we're going to take the value in our parentheses, raise it to 1825, and then multiply by 13,200. So that's going to give us $16,122.34. So see how with the same interest rate, okay, as you're compounding more often, you're earning more money. It's not a significant amount of money, but the more money you have in the account, then the more significant it will be, and the higher the interest rate. All right, so that is all of 4.1.